I'm hoping by now you've familiarized yourself with the polar coordinate system and all the conversions from Cartesian to polar coordinates and the from polar to Cartesian. And that also comes from that relationship between x, y, r, and theta. So hopefully you're understanding how x, y, r, and theta are related, and that's going to really help you be able to graph these Rose curves, the cardioids, lemmason, and the lemniscate. I'll let you read through the calculus and polar system information here. Probably would be best to do that after we do the notes. But also then once we get through the polar, you'll want to make sure you, as you're getting ready for the Chapter 10 test, that you familiarize yourself with the parametric and vector sections. You make sure you're focusing on these key points, and then also from the polar. So we're going to talk about polar today and polar on Wednesday, and by the end of the week, hopefully you'll be solid with polar, and then you'll be ready to take the test a week from Friday. Of course, this is the year 2014, so who knows what's going to happen next year. Let's go ahead and start with this guy right here, computing the slope of a polar curve at a point. So the parametric formula for slope of a curve, well, we already know that dy dx is the slope of just a curve just as y as a function of x. But if x and y are defined parametrically, then we know that dy dx, still the slope of the curve at a point, is defined to be dy dt over dx dt. Okay, well, in polar, we have the same idea where we have a dy dx. In other words, we've got this polar curve out there in the middle of nowhere, and it comes around like that, let's say. And it still has everywhere along the way, you could draw a tangent line to the curve at any certain point. Sometimes the tangent line is supposed to be nice and smooth. Sometimes the tangent lines are vertical, so the derivative wouldn't exist. Sometimes the tangent lines are horizontal. But nevertheless, we still have a dy dx, and as you might even guess, the dy dx, if r is defined as a function of theta, I should have defined that first here, where x and y are both functions of t, so f of t, y is g of t, let's say. Okay. Anyway, r is a function of theta. Well, dy dx is defined to be dy d theta over dx d theta. Okay, so we have a polar formula for the derivative at a point, or I should say the slope of the tangent line at a point. And that's exactly what we're trying to find, the slope of a polar curve at a point. So let's go ahead and calculate a couple of these. Let's do our first example, leave that there. And our example 1, find the slope of r equals 1 plus the cosine of theta at theta is equal to, let's say 0. Okay, so we'll just start off with a pretty basic one, and if we want to, which I think it's important, we could start off with, actually this is going to be r equals, let's do theta equals not 0 because it's going to give us an undefined slope. Let's do theta equals pi over 2. Okay, sorry about that. So anyway, if we draw the graph of r equals 1 plus cosine theta, we know that, we start off here. So if you do an r theta chart, you start off with theta equals 0, you get 1 plus cosine of 0, so 1 plus 1 is 2. Okay, and then if we replace theta with pi over 2, we get cosine of pi over 2 is 0, plus 1 is 1, so we get the point 1 pi over 2. And then from class, hopefully you now remember that the graph of this polar curve, now it's not perfect, but you got the idea here. This is a smooth transition here, like I said the other day. And what we're trying to find is the slope of the curve when theta is pi over 2. So it looks like it's going to be somewhere around 1, or maybe a little less than 1. I would guess maybe 1/4 or so. And but it does not look like that's where the tangent line will be horizontal. So let's go ahead and take a look and see how we do this. Well, again, dy dx is equal to dy d theta over dx d theta. Now, it kind of looks not as, it doesn't look very involved yet, but watch what happens. If we remember, let me see, where should I put this? I'm going to put this right here, where y equals r sine theta and x is equal to r cosine theta. Okay? Well, look what's going to happen. dy d theta would be dr sine theta d theta. So it starts expanding right before your eyes here. And dr cosine theta. Well, we don't like those r's in there either. So we're going to replace r with what r is equal to. So that's this guy over here. Okay. So in the numerator we have r, which is 1 plus cosine theta. We still have to multiply that by the sine of theta. And then downstairs we have, again, r, which is 1 plus cosine theta. And we multiply that by the cosine theta. Because, again, the dy d theta is dr sine theta, d theta. And r is this guy. So we still have dr sine theta and dr cosine theta. So now we have everything in terms of theta, and we don't want to necessarily have to use the product rule here. So this is going to take a while. That's why I got a few boxes down here. We're going to distribute the sine of theta to both of these terms here. So we're going to rewrite what we're taking the derivative of in a way that makes it easier to actually take the derivative. So yeah, this is the very first example, I realize that, but the concept, meaning the concept shouldn't be that bad, where again, we're still trying to find dy d theta over dx d theta. So there's just a lot of algebra here. So just be careful. Sine theta plus sine theta cosine theta, okay, over d theta. And then, I shouldn't say over d theta, it's d theta of that stuff. And then d theta, derivative of cosine of theta plus cosine of theta times cosine of theta, so cosine squared of theta. Well, now we're ready to go ahead and take the derivative of the numerator, and the derivative of the numerator would be the derivative of the sine is cosine. Now we have the derivative of a product here, so the derivative of this product would be the first times the derivative of the second, which is negative sine theta, plus the second cosine theta times the derivative of sine, which is cosine, so it's cosine squared of theta, all over the derivative of cosine, which is negative sine, plus the derivative of cosine squared, which is plus 2 cosine theta times the derivative of cosine theta, so negative sine theta. So number one, it's important that you can do the product rule quickly, and that you can also remember what the derivatives of the sine and cosine are. So that is the dy dx, okay? What we wanted, though, was we wanted dy dx at the moment when theta was equal to pi over 2. Now, fortunately, there's nothing else to do other than plug theta over 2 in, or sorry, pi over 2 in for theta. And the good thing is that most of these terms, or some of these terms, are going to go to 0, and the other ones are going to go to 1. Okay, so let's see. That's going to be dy dx at theta equals pi over 2, which is this stuff at theta equals pi over 2, which is equal to, now we're going to put pi over 2 in for every theta. Okay, well, the cosine of pi over 2, that's going to go to 0. The sine of pi over 2 is 1 times negative 1. So 1 times negative 1 is negative 1, plus cosine squared of pi over 2, which is 0, over negative sine of pi over 2, so negative 1, plus 2 cosine pi over 2, that's 0 times whatever, and so we get negative 1 divided by negative 1, we get 1. So I was wrong at my guess of 1/4, but I was right in that the slope is positive, and it's not 0. So summarizing the one example that we just did, we have r equals 1 plus cosine theta, and the graph of the function looks like this. At the precise moment when theta is equal to pi over 2, the dy dx, which is this big, long, ugly formula here, expression I should say, at pi over 2 is equal to 1. So all that work for that 1. Okay? Now more than likely you're not going to get a problem like this, but it's important that you know all parts of this problem, because you never know what kind of problem you're going to get. You never know if you're going to get, well, what's the formula? What's the formula without any r's in there? You just never know. Maybe you'll get the formula and you'll be asked, what's the derivative? What's the slope at theta equals pi over 2? You just never know what you're going to get. The most important thing that you guys can know here is how you get from dy dx to this guy right here. There is a formula in the book if you wanted to memorize that. I don't like to memorize it because if I forget one thing, then I'm toast. So don't be toast. We'll see you in the next video.